this is also a pleasure for me, particular pleasure, to announce our today's speaker, who is Professor K Pachucki. Some of you probably know him very well, maybe even better than me, although I had the pleasure to work with Krzysztof, at the Institute for many years. Krzysztof, as you know, is a worldwide expert in very precise calculations of atomic levels, particularly in light atoms and light molecules. His calculations are more precise than experimental data. That is absolutely unbelievable. And of course, he is using extremely complicated calculational schemes based on quantum electrodynamics, or quantum electrodynamics-driven corrections to the classical Schrödinger equations. And for his achievements, he got something which we call popularly the Polish Nobel Prize. He got this year the prize, the most prestigious prize of the Foundation for Polish Science. I think that's the correct name. And it is also my pleasure to have here with us Professor Andrzej Trautmann, because I think that such a small unit like the Institute of Theoretical Physics, it's really amazing that such a small unit got 2 prizes in a row. I mean, it happens once at the Center for Theoretical Physics, our colleagues got 2 prizes in a row, but in our case, it's really the event. And let me also mention that we have 5 laureates. We, as the faculty, 5 laureates of this prestigious prize, and I think that this is a Polish record. So, let me tell you briefly that Krzysztof calculations, are not only very precise on the atomic scale, but of course they are so precise that they are able to probe the structure of nuclei, and in particular, of course, are sensitive to certain quantities like radii, quadrupole moments, etc. And this is the subject of today's presentation. So, Krzysztof, the floor is yours. You've got 45 minutes.
So, thank you for the introduction. From time to time, we are asked by our relatives or by our colleagues what we are working on. And when I am asked, I always had a problem to explain what I am working on, what it can be used for. In my case, always difficult to explain. So it happened that a month ago, our system of units has been measured, so now I have an answer that we can help to make a good weight, or we can help to make a good thermometer. So, or to understand, because what was this change about? The change in the system of units, international system of units, is the following: that we no longer rely on artificial artifact like this 1 kilogram weight, which has been placed in Sèvres, close to Paris, and it was a definition of the kilogram. And the problem was that this definition of the kilogram was changing in time, because this device always evaporates. And one of the most difficult problems was how to construct a new weight, which will represent 1 kilogram. And the problem has been solved that we found a practical way, physicists, have found a practical way to transform the value of the Planck constant to the value of the 1 kilogram. It is not so easy, this transformation. It requires a quite complicated balance. It's called Kibble balance. But it can be done. It can be done in a repeated way. By several, it was done. So now, instead of this 1 kilogram weight, we set the value of fundamental constant. And this is the physicists who And these are the physicists who allow to transform this value of fundamental constants to the physical devices which are used in every shop, because almost every shop requires to measure the weight or to measure the temperature. Maybe not the shop, but we also very frequently measure temperature, and physicists, what they can do, they can measure temperature very accurately. And so we, in the middle of November, we decided, means our scientific community has decided that the definition of the Kelvin, the definition of the kilogram, everything will be based on fundamental constants, like means in Planck constant, electric charge, Boltzmann constant, and Avogadro number. And these constants are now set, and from these constants we derive the weight or the thermometers. We describe the thermometers. So this is, I would say, application of our work, of our research. If I am asked by some physicist, then I can give an answer more specialized. So we are working, or some of our colleagues work on testing fundamental interactions, and how we can test the fundamental interactions. One of the ways is, for example, to determine constants in different ways. We can determine, for example, fine structure constant from the electromagnetic moment, also from the muon magnetic moment. It's not the most accurate, but anyway, it can be done. We can also determine the fine structure constant from the helium fine structure, just by comparing the calculation with the experiment. Or one can determine fine structure constant, which is now the most accurate method, based on the measurement of atomic recoil. I mean, atoms absorbs photons, and since it absorbs the photon, the total momentum has to be conserved, so it gains the momentum. If it absorbs many photons going in one direction, but emits in the other direction, it gains energy or gains momentum. It can be measured. And this is the most accurate determination of the fine structure constant. And these are the most recent results, a summary which I have copied from the recent Nature paper, by whom I should mention by these authors. And the fine structure constant was measured from the from different. I have to use this one. This value is moment. This is the value which is the famous one is from the magnetic moment of the electron. One can calculate the magnetic moment of the electron from first principles because there is no any. It's almost a pure QED effect. The strong interactions or the weak interactions are much smaller, are very small. They can be estimated, and by comparison of experiment with calculation, one obtained the fine structure constant, which is of the order of 10 to minus 10, 2 times 10 to minus 10, relative accuracy 2 times 10 to minus 10. Oh no, this is the G minus 2. And the other measurements rely on the recoil of measurement of the atomic recoil of cesium and rubidium. They are slightly in disagreement, but at least at the order of few times 10 to minus 10, different methods of determination of fine structure constant give the same value. And this we can interpret as a quantum ergonomics works at the precision level of 10 to minus 10. We don't know what can be the higher precision, but at least 10 to minus 10 precision, quantum ergonomics works pretty well. What I'm working on is I'm trying to compare the calculation of atomic energy levels or molecular energy levels with experiments, and to find out the discrepancies, or to test to which precision we agree, or if there is a disagreement, it can be due to fundamental constants, or it can be due to the new physics. The reason is, the reason that we study the simple atomic system, in fact, there are two reasons. One, atomic systems like hydrogen, or hydrogen molecule, or helium, can be calculated very accurately. And we can control the accuracy. From other side, it can also be measured very accurately. The spectroscopic measurements, the measurement of frequencies, can be accurate up to 18 digits. What is interesting that one can construct atomic clocks, something which gives you the measure the time flow or the frequency. And the precision of such atomic clock is so high that if I shift it by 1 centimeter up or down, I will see the change of the frequency due to the gravitational redshift. It's enough to shift the atomic clock by 1 centimeter. So the spectroscopic measurements can be very accurate. And this gives the potential that we don't need to go to the high energy like it is done at CERN, that they can go to, I don't know how much, to 14 TeV. But we can, instead of going to the high energy, we can go to the precision. And by comparing the predictions with experimental precision, we are looking for some new physics, some new effects. It can be some unknown forces, or it can be some some unknown effects. A typical measurement in hydrogen is 1s2s. It is performed at around 10 to minus 14, on 10 to minus 15, 10 to minus 14 precision. And the only problem is that we cannot compare our theoretical predictions to the 1s2s because there is no fundamental constant at this precision. We use the reverse way. We use this transition to determine fundamental constant, like the Rydberg constant. But to determine the Rydberg constant, we need two transitions, not only one, because there are two unknown parameters in hydrogen. These parameters are the Rydberg constant, which Rydberg constant gives you the transition from the atomic units to the measured units, which is the hertz. And this constant, which transform atomic units, dimensionless atomic units, to the hertz, is the Rydberg constant. Another parameter is the nuclear charge radius. It's a very small effect. I will describe in a moment what I mean by this. But we need two transitions, and the problem with the hydrogen is the second transition, because in hydrogen there is no any narrow transition, which can be measured with comparable accuracy. And all these problems with the proton discrepancy most probably come from the fact that we cannot find another transition, that we cannot measure so accurately any other transition in hydrogen. And as I mentioned, there are two measurements of the proton charge radius, one in hydrogen, I will explain some other transition, also in the muonic hydrogen, which I will describe in a moment what I mean by this. But these two measurements determine the proton charge radius, which are, these values are discrepant. They're discrepant by 4%. So far, we don't have explanation. I will explain the possible reason, because we have now much more experimental data than a few years ago, and we think we now understand where this discrepancy comes from. I will describe this. But let me mention that there are several attempts to verify the discrepancy by studying a system which is very similar to hydrogen, namely the helium atom, but with 1 electron less. We take the 2-electron normal helium atom, which consists of 2 electrons. Take the 1 electron out, so we have a hydrogen atom. And this is even better hydrogen atom than what I mean better, because alpha, the nucleus of helium, is spinless. So there is no splitting of energy level. It's very similar. I would say is very good. The only problem is that 1s2s transition is in the very far ultraviolet. We don't have lasers at this frequency. So one has to make lasers, and this is the main problem. Once we have lasers, or with enough intensity, we can drive 1s2s transition and check whether this discrepancy comes from. It can be a kind of the smoking gun experiment, which we verify. But I will present some some other measurements which will indicate where this discrepancy may come from. So there are, in summary, just a summary at the beginning, but I will again at the end present another summary. There are two ways to determine the proton charge radius: from the spectroscopy of hydrogen atom, from the spectroscopy of muonic atoms, and the discrepancy of the order of 5 sigma. It changes in time because there are a number of experiments for hydrogen, and for hydrogen so far, not for muonic hydrogen. In fact, there is also a third way to measure the proton charge radius from the electron-proton scattering. All these methods agree, all these electronic methods agree. Electronic, but I mean electron-proton scattering or normal Sometimes I would call it electronic hydrogen, but maybe it's better to say ordinary hydrogen. All of them agree. This codata value is, it should be a statistical average. Somehow it is not visible from this, but maybe we include some other data as well from the deuteron, from the deuterium. Anyway, there is a large discrepancy. And what is interesting, that it cannot be explained by any simple modification of quantum grammatics. In fact, it cannot. One can, if you add something to the standard model, any new interaction, then one will spoil the G-2 of the muon, or another test. So it is really discrepancy, because if both experiments are correct, the hydrogenic experiment and main hydrogenic experiment, we will have a series of problems to understand, even to build a better theory which will describe this, because every better theory will spoil other tests, or will require a very fine-tuned tuning of parameters, which is very artificial. Please.
Namely, you quoted the number of hertz, 18 digits or something, while the definition of a second, which is 9 billion cycles per second.
It's 10 to minus 15. It's 10 to minus 15.
Yes, 9 billion. How can you measure hertz?
You don't measure hertz. You can compare one frequency with another frequency. So you can compare one clock with another clock, with another transition. You don't need cesium frequency standard for this. You can build your own frequency standard based on Waitabrium and compare with another clock.
So effectively use different standard than cesium standard.
Yes, because cesium standard is not
and that will be
sufficient.
changed by definition of a second
Not
in the
at this
future?
moment. Such a change is planned, probably in about 10 years.
Okay.
But it is, yes, and people are working on it.
One doesn't use cesium, one uses different clocks to compare this.
Yes, this is the spatial clock based on Waitabrium. It's a lattice clock made of Waitabrium atoms.
Okay.
Indeed. Maybe I should mention this. And now let me present a little more details how this electronic ordinary determination of the proton charge release from ordinary atom flux has been performed. In fact, as I mentioned, there are many transitions. Except 1s to s, all the other transitions are wide. In fact, this is the accuracy of the measurement is shown by these bars. In fact, each individual measurement, for each individual measurement, the discrepancy is of the order of 1 sigma. It is 5 sigma only because of the statistical average. So if there is a systematic error in these most accurate measurements on hydrogen, this would explain the discrepancy. And this is what I would like, this will be my conclusion, that I'm going ahead, that I would try to prove, I would demonstrate that it is in fact the case that that there was some systematic shift in most of these measurements, and this is not the single mnemonic hydrogen which is wrong, it's just all these 10 or 15 measurements in hydrogen which are incorrect. I shifted by 1 sigma because of some systematic shift. I will try to give arguments for this.
Are the measurements incorrect or the average is incorrect?
Please repeat the question.
Are the measurements incorrect or the average of them?
Look, if the measurements are independent, then the statistical average is fully justified. They are not independent, and then we take them into account. So we don't perform a statistical average, we make a weighted average. Mikołaj, to get this mean value, one takes into account the correlation between different measurements, if there is any. In fact, there are, and one takes into account. But some of these measurements, it's simple. It is much easier to say that we perform a statistical average, but in practice, it's much complicated. Good. So now, why we study the hydrogen? Because hydrogen is very simple to calculate, and we learned from I don't know which class in the high school that energy levels are use the Bohr formula. But in fact, the Bohr formula is the first approximation. There are many corrections on it. And all of these corrections are described by this delta. We don't go into details. They can be calculated for first principles. What cannot be calculated is the value of this coefficient. This has been taken from the experiment, the mean square charge radius. But what we can do, we can calculate the coefficient in front of the R square. In fact, this is the wave function of the region. It can be calculated easily. And what the shift due to R square comes from? And the shift comes from the fact that if the proton has some charge radius distribution, which is not delta, but has a finite charge distribution, like this, then the Coulomb potential is modified at the distance of 1 Fermi, approximately 1 Fermi, and instead of going to minus infinity, it goes to some value. And this shifts slightly the energy levels. The shift is very small, but because of the high precision of experiments, it can be detected. By measuring the shift, or in fact, we don't measure the shift, we measure the absolute transition energies, but you can measure it from two different transitions. From this, we can determine the charge radius. And now, having this hydrogen atom, we can ask the question, how much we can now consider the very similar atomic system like muonic hydrogen. We take the electron out and replace electron by muon. The only difference is mass, because the standard model says that muon has to have the same charge. It has to interact in the same way with the proton, with any other particle. It's a so-called universality of fundamental interactions. So it means that you can use the same theory, almost the same theory, or the same equation, formulas to describe the muonic hydrogen. And we do so. The only difference is that the mass is 200 times heavier, so the wave function shrinked, or the volume of the, if there were the volume of the muonic atom is 200 to the third power smaller, so the smaller sensitivity charge radius. And in the case of muonic hydrogen, the finite size is a significant portion of the Lamb shift. What we call the Lamb shift is a splitting between 2s to pi. It is of particular importance because according to Dirac equation, it is 0. So it has to be something else. And something else is the muon self-interaction and the vacuum polarization. Here, the dominant contribution comes from the electronic vacuum polarization. The electronic vacuum polarization modifies simply the interaction between the electron and proton. This modification is very small for electronic atoms, but here it's very significant, so it gives most of the shift. And the finite nuclear size is 10%. 9% of this. So it's a very significant effect. For this reason, by measurement of the Lamb shift, one can determine the proton charge radius very accurately. I mean, as accurately as we can estimate some nuclear polarizability, the proton polarizability. In fact, this is the main problem here, to estimate properly the proton polarizability.
What is the correction for 2p? I know that 2p has 0 at the exact 0, but since the proton is not.
No, but I will repeat the question. If you say, I will repeat the question. So what is the effect for 2p state? And Krzysztof asked the question, because since the 2p wave function vanishes at the region, is it shifted? In fact, it is shifted only by the electronic vacuum polarization. So this is the, what is interesting in the muonic hydrogen, which I should mention, is very good that you asked this question, that Coulomb potential is modified by this electronic vacuum polarization. It so happens that the Compton wavelength of the proton, of the electron, is of the size of the Bohr radius. And this means that all this, that the energy levels are very much shifted by electronic vacuum polarization, p states as well. Maybe not as large as the electronic state, as the S state, but it's also shifted by the vacuum polarization. So it's very much sensitive, but it can be calculated. We can calculate what is this potential and solve the differential equation numerically. This is trivial, or use perturbation theory. So p states can be calculated much more accurately than S states.
Yes, but P state also has, even if it is 0 at 0, if you have a ball and not a delta function, P in principle overlaps with a proton, even a P state.
Yes.
How large is it?
It is at least, because it is relativity correction of the wave function, so it's alpha square, 10 to minus 4 correction, proportional to R square. It can be easily accounted for, because, but you are right, there is such effect. But much more important effect is this nuclear proton parasitivity correction. This is something which is, it cannot be calculated from first principles. What this means, but let me, before explaining what this is, let me describe the leading effect. The leading effect is just, as I mentioned, vacuum polarization, but one has to include also the two-loop vacuum polarization. It's conventionally called Callan-Sabry because they were the first to calculate this. Self-energy, the muon vacuum polarization self-energy. But in fact, these are the most important corrections. All other contributions are smaller than this discrepancy. So this demonstrates that the discrepancy is really large. And what is very problematic is the proton parasitivity. Sometimes it's called two-photon exchange. In fact, it can be expressed as a, it can be explained as the fact that proton can be excited or can emit a pion, or it can be anything else between the two interactions. And this proton parasitivity correction cannot be calculated from principles. We can use the inelastic scattering and dispersion relations to calculate the real part and then calculate the M-shift. It requires subtraction terms. There are several uncertainties. For a long time, we thought that maybe we are not able to calculate it very accurately. So this uncertainty is not correct. But to explain the discrepancy, the whole effect has to be 10 times larger. So it is not the uncertainty has to be 10 times larger, but the whole effect. So it is very difficult to predict. As I mentioned, most probably it is on the electronic hydrogen.
Is it renormalization scheme dependent, these two photon exchanges?
I did mention that all the calculations in the quantum programming are performed at the q square equals 0 by definition. So if you say alpha, I always means alpha at q square equals 0. This is the fundamental constant, which is given in textbook and probably in every textbook in high school, and then it's just alpha at 0.
So you don't have any problem of renormalization scheme dependence of a loop diagram, which is normally the case.
Look, we are using the experimental cross sections. So
okay.
There is no time. What you mean is the fact that we have to include the fact that we include vacuum polarization is just the inclusion of the Feinstein constant depends on q square, but we use perturbatively, so it's under control. And now, most of us would think that the single experiment is wrong in the muon hydrogen, because it's just a one measurement against 15 or 20 measurements in hydrogen. But let me explain that this is the line which has been observed. This is the water line which is of known frequency, and this is the value of the proton charge radius. So this peak should be there if the proton charge radius has the value predicted by this hydrogen spectroscopy. So it is on the other side of this water line, so it means that cannot be a mistake, experimental mistake, because this line has to be shifted there to be in agreement, or somewhere there, in fact. So it's a general argument that this measurement, there is no any loophole in this measurement. At least nobody has found any loophole in this measurement so far. So let me now repeat. In fact, there are two measurements in hydrogen. There are two transitions which has been measured: 2s to p1/2 and 2s to p3/2. The angular momentum, orbital angular momentum, adds to the spin and gives 3/2 or 1/2. And there are two p states, and both of them give very close results. This d is the deuterium value. I will explain that this has been shifted. I will explain what is the reason of the shift. Now all of them agrees and sits on the line here. And now, since we have a disagreement for hydrogen, let us check what may happen in other systems. The closest system is deuterium, and such a measurement has also been performed. The difference between the hydrogen and deuterium is very small. Only the nucleus is heavier, but it can be easily accounted for. But also nucleus, from the point of view of muon, is a weakly bound system of proton-neutron. It's a very weakly bound system. This means that this muon strongly affects of this deuteron, and this has to be accounted for. So, in fact, we spent several years to study this, and now we agree perfectly between the two different groups, agree very well. And I will explain that we also agree very well with the experiment. But I will explain later what I mean by this. So they are the same diagrams. Two-photon exchange in between deuterons excited. It can be excited by ionized or dissociated. What is the proper word? What do you do with the nucleus if proton is separated from the neutron? What is the proper word? Dissociated? Ionized? Dissociated. Okay. But I would use it for molecular systems, dissociated. But for nuclear, I don't know what is the proper word. So one has also take such a. They can be calculated, and they give this. The uncertainty is much larger. Anyway, it is. It can be given, presented as uncertainty, what is most important. And again, this similar coefficient times the deuteron charge radius. And this two-photon exchange, as I mentioned, one can use, because hopefully we know very well the proton-deuteron potential, because from the proton-neutron potential. Because there are many proton-neutron scattering, and they can be represented in terms of some potential, some effective potential. One can use this potential to calculate the deuteron, and it agrees pretty well with the predictions for the binding energy, for the quadrupole moment. So we think we understand very well the deuteron. No, but they can be accounted for. They are small. We have estimated them. No, we have calculated them. Three-photon exchange is much smaller than this uncertainty. But it's important. Three-photon exchange is important. But also other corrections which are important, I will mention in a moment. So there are, one can, in fact, we determine this porosity correction, porosity corrections, and then, and from this one can determine the charge radius. In fact, this is already outdated, so I will not concentrate on it. Let me go on and present the result. That the graph is still old, and since I have a pretty good student, so I gave him the problem to calculate some additional correction, and in fact, he found out the correction to the muonic deuterium porosity, which comes from the fact that I have to return. No, this is up. I have to return. If this additional correction is if we had the electronic vacuum polarization on one of these electrons, one would think that this is alpha over pi correction, because usually, but in fact it's logarithmic enhanced. And if one adds this, it exactly shifts this deuteron charge radius toward this line. So there is any disagreement with the between muonic deuterium and muonic hydrogen. All of them are in agreement on this line.
Is the fact that a deuteron has a quadrupole moment included in this business? It is very small quadrupole moment due to tensor interaction.
Yes, the quadrupole moment, in fact, for the deuteron is pretty large. But what has been measured is the transition between 2s state and 2p1/2. For these two states, quadrupole moment gives 0, because it's total speed, total angular momentum is 1/2. For such a state, because quadrupole moment is a tensor like of L equal 2, it has to vanish. It vanishes.
The angular momentum of the nucleus does not coupled to this?
Through the second order correction, it can. Yes, we haven't. We have. I don't recall now how much is this. It can be the quadrupole moment, the second order. So it's a second order correction to quadrupole moment. So this would mean the coupling of the angular momentum of the nucleus to the angular momentum of the muon. Let's say we haven't included this effect. We don't know. So I don't know. I don't have an answer. I would guess it is small, but I don't know. So Marcin, let me explain how we compare the deuterium charge with the proton charge radius. It's not so obvious. Take the hydrogen, electronic hydrogen, and deuterium. One can measure very accurately the isotope shift between hydrogen and deuterium. From this isotope shift of 1s to s transition, because 1s to s is a very sharp transition, 1s to s in deuterium, we take the difference. From difference, we have very accurate also difference between the deuterium charge radius and proton charge radius, and this is fixed. So we have this difference, so we can now use the muonic hydrogen value to obtain the deuterium charge radius from this difference. So all of them are in agreement, and this is this value of this difference, which is obtained from the, also including this free-photon exchange. And now, what is new are the new experiments, which, to my opinion, solve the problem. For the last, during the last 2 years, there are several experiments. The 2s4p transition, 2s4p transition, which has been measured in Garching, in muonic or Garching, and it happens to be in agreement with the muonic value. It has a large uncertainty because it's a 4p state, which is white. It has been measured there. There's another measurement, Toronto, is a 2s2pi measurement. It's a classic lamp shift. The person who has done this measurement, Eric Hessels, has found a mistake in the previous measurement of Landin-Pipkin, a famous measurement, and performed a new measurement. It also got an agreement. There is another measurement from the electron-proton scattering, which is performed Jefferson lamp. It is also in agreement with muonic hydrogen. In the meantime, another group in Paris has also measured 1s3s, has measured 1s3s, and this 1s3s is again in agreement with the electronic hydrogen. So now, we rather have a discrepancy between the measurement performed in Paris and in Munich. One can interpret this. But if, what is most important is that this Toronto measurement is really independent, is 2s2pi, is on the other side, and Jefferson lab measurement. The Jefferson lab measurement differs from all the previous electron scattering measurement by the fact that they performed measurement at much smaller q². It's much smaller momentum exchange. And it is then much easier to perform extrapolation to q² equals 0. And they are in agreement with it. It's a preliminary result. It's not yet published. It has been announced 2 months ago on the conference. And this is the value. So now we have rather situation that there are different measurements. There are electronic measurements, electronic hydrogen measurements, which are in agreement with the muonic hydrogen. There are also electronic measurements in agreement with the previous measurement, and the situation is unclear. Most probably, something is wrong with this hydrogen measurement performed in Paris. So since we have a disagreement with the hydrogen, in muonic deuterium, maybe it will explain, but this comparison between electronic hydrogen and muonic hydrogen shows the potential of this method, that because we can calculate the system very accurately and compare, we are sensitive to mistakes in the experiment, or we are sensitive to some new theory. So the advantage of other system is, in comparison to hydrogen, that, for example, in helium, there are many transitions which are very sharp, which can be measured much more accurately. It can be measured with 10 to minus 12 precision. I already, Krzysztof asked about the helium plus. Helium plus, as I mentioned already, is very much similar to the hydrogen. So there's only one transition, 1s2s, which is very sharp. And there are two laboratories which has received ERC grants 2 years ago to perform the measurement, one in Munich, another in Amsterdam.
But that's still not yet measured, muonic versus electronic with helium plus.
Munich helium is already measured. It's not yet
Helium
announced.
plus, helium plus, I mean. So in analogy to
Munich
hydrogen.
helium is just mu plus. Munich helium means nucleus and muons, no electrons.
Yes, but I mean helium plus, which is in analogy to
Yes,
hydrogen.
the helium
Yeah.
plus, you mean electronic plus, the one electron.
One electron and one muon, whether
Yes.
they have difference
Stop.
in
You
radius.
mean alpha, one muon, and one electron.
Alpha 1 muon, period. Alpha 1 electron, period.
Okay.
Whether there is a difference in the radius.
Okay, so this I will present some results. Just
Okay.
wait. This is what the talk is about. I will present the results. So far, we don't have measurements in 1 electron helium. We have a measurement in 2 electron helium. Because the measurements in 1 electron helium are too difficult. For 2 electron helium, the theory is much more difficult, but still we can do the key. I will present the results for calculation. The advantage is that there are transitions which can be measured very accurately in 2 electron helium. So we try to do the calculation. And sorry for this slide, because I would like to slightly present I try not to present the formulas, but somehow, because it's the heart of what I'm working, I have to present a little bit of formulas. So for hydrogen, we can solve Dirac equation, almost done. For 2 electron system, it's a little bit more complicated. The idea is the following, that we can take the energy levels and perform expansion in the fine structure constant alpha. The fine structure which I described at the beginning. Perform expansion, calculate every coefficient separately. How we do the calculation? By representing every coefficient as an expectation value of some Hamiltonian. The non-relativistic energy is solution of the non-relativistic Hamiltonian. We know it perfectly. We can solve it with arbitrary precision. What is interesting, helium, one cannot do it analytically, obviously, but numerically, it is rather easy to get 40 digits for the energies. So from numerical point of view, helium is very simple. This is not a problem from numerical side. It's only a problem to derive the effective Hamiltonians. So this is the relativistic correction. And what I mean, this effective Hamiltonian, and calculate E4 as expectation value. And it works for all other coefficients. It's very simple. Maybe not as, the format is maybe not as simple, but the method works. Look.
Okay.
Yes, but this is exact. I mean, we can prove in QED that the expectation value gives exactly the E5 coefficient. E6 is too complicated to write, but it can be done. And also E7. And now the example how this expansion works. That this is the expansion alpha, this expansion mass ratio, because we have to perform the, in fact, there are 2 parameters. One is alpha, another is electron nucleus mass ratio. Perform expansion both and calculate all these coefficients. This forms a triangle. We can sum up. This is the theory. It agrees very well with the experiment. In fact, with this experiment, with this a little less. But it shows the accuracy is still not sufficient. The problem is that we haven't yet reached the accuracy sufficient to get a charge radius. It will take another 2-3 years. We have received a grant for this, and it's working hard, but it is really not yet. We need another order calculated alpha 7. It is not yet done, but it can be means in 2-3 years, maybe we announce the result. But we can compare helium-4 with helium-3, the isotope shift. And we can compare with the muonic values. And this is interesting. Probably this is the most interesting slide. Please.
Could you wait for a moment?
On the previous slide, there is E2 and E4, and why is the E3 missing, or is it just like missing from the formula?
Okay. Yeah, this is a frankly to ask question. I will use the board. I would give a naive explanation. So if you consider the relativistic kinetic energy, is equal p square plus m square, and perform a Taylor expansion. So it is m plus p square over 2m minus p4 over 8m cube plus something I don't remember, p6. There is no p cube term. And P5 is the QED correction, self-interaction, so it doesn't come from this, it's another source. But there is no anything between the non-relativistic and the leading relativistic because because the expansion only involves even powers of alpha somehow.
Or the finite size correction as well?
Finite size goes with the wave function of the region, is alpha cube, and one photon exchange, which is alpha 4. Then it goes with alpha 4.
Okay, thank you.
And then correction to it, alpha 5. Yes, but the leading is alpha 4. Okay. But what this table is for? I would like to demonstrate that this expansion in fine structure constant is a very good approach because it allows to control the intensity. We haven't calculated alpha 7 accurately enough, so we estimate from hydrogenic value, and alpha 8 is small. So it's somehow, if most of the groups are not using expansions, some use some effective Hamiltonian, some different approach, but all other approaches don't allow to give an estimate of the uncertainty. It's somehow, when you look on the papers written by quantum chemists, they give energy levels much more accurate. They give 10 digits or 16 digits. I mean, the size of the double precision on the computer. But doesn't mean anything about the accuracy of this result.
What is the main source of this 1.0 in
The fact that we use the we use the hydrogenic values, so it's approximate calculation, and this is our estimation. What we think is the estimation of the correction, which is not calculated, based on the hydrogenic values.
But you will calculate it in this grant, yes? You will
Yes, I'm going to calculate this in a couple of years. This is the idea to calculate.
And what is the expected accuracy that you can
expected by the
achieve?
alpha 8? You do the same with alpha 8, based on the hydrogenic value, because now the alpha, it will be of the order of 10 kilohertz. This is 1 megahertz, 100 times smaller, 10 kilohertz.
Okay.
And this is sufficient to get the charge radius. Compare. Since we are not able to calculate determine the charge radius, we can determine the charge radius differently, helium-4 and helium-3. Okay, before this, sorry, I have forgotten. Let me present some comparison with various transitions. Most of them we agree. Somehow, for all the transitions which involve these states, we have there is a 1.5 megahertz discrepancy. It's sometimes 1 sigma. We don't know the origin of this discrepancy. But for most of these transitions, especially to triplet S to triplet P, the argument is very good. But let me now go back to the finite size. This is somehow answer to Krzysztof, that if we are able to determine with 10 kilohertz this transition, then we can get 1.5 to 10 minus 3 accuracy for the charge radius, which is quite good, if it works, if the method works. And now the results from the isotope shifts, which is also not yet announced officially. No, now it is only for helium-4. This is the not yet published result, but anyway, it's a result from the muonic helium. Comparison with the electron-protons, with the electron-helium scattering, pretty agrees. In fact, we believed that, people believe that such a measurement of muonic helium has been performed 50 years ago, but this experiment was wrong. They observed some different line. We don't know which one, but this muonic helium measurement, which is much easier than muonic hydrogen, which was performed 50 years ago, was most probably was incorrect. And there is also, no, in fact, I don't know what is Otterman measurements. The most important that this muonic helium agrees with the electron alpha scattering. It shows that something is wrong with the, possibly with this electron proton scattering as well. And now the result for the muonic helium. And this is a very surprising result because the muonic helium, we can determine, for the isotope shift, we can determine the different charge radius for the muonic atoms and also for several transitions in helium. Oh, I haven't written this. What is transition? One can measure the triplet SP transition or triplet singlet S transition. In fact, there are several sharp transitions. And in fact, for every transition, the charge radius difference is different. We don't know the reason. Most probably it's on the experimental side. In fact, it's easy to make a mistake. For example, there was a measurement in 2012 which happened to be incorrect because a Chinese group has repeated this measurement and we obtained the wrong charge radius. This is the triplet S to singlet S, which has been corrected by another measurement of the same type. It also shifted. This is the electron-proton scattering for the difference. It's very wide. So in fact, we don't have, for the charge radius difference, we have such a situation that all different determination give different charge radius. Muonic helium, 2 triplet S to singlet S transition, and 2 triplet S, this is 2 triplet S to, and 2S to P transition. All of them give a different result. We don't know the reason. I'm almost sure that the theory is correct, because it's most probably the experiment. We are waiting for the new experimental data. They will come in 2-3 years, and then we can compare which one is correct. Let me now pass to the heavier elements. That a similar measurement and calculation we have performed also for lithium, also to measure the isotope shift. And from the isotope shift, what is the advantage of this atomic spectroscopy methods? Because we can measure also the isotope shifts for short-lived isotopes, which lives for microseconds. Oh, maybe, let's say milliseconds. For such a long-lived isotopes, one can perform the spectroscopy and determine the charge radius. So very interesting is lithium-11. And for all these lithium-7, 8, 9, 11, we can compare with lithium-6 and obtain the charge radius, change of the charge radius from the isotope to isotope. The same from the beryllium. And this is important to test the nuclear models. I don't know these nuclear models. For me, these nuclear models are much too complicated. I simply don't understand them. I don't understand the mathematical basis, in fact. Anyway, they're able to predict the results, and this also includes the measurement also includes the beryllium-12 and beryllium-14. No, I'm not sure if the beryllium-14 is measured. No, it's not measured. These are only the measured values. The most recent one, which is not yet announced, is boron. It's a 5-electron system. It's the calculation for 5-electron system took us more than a year to solve the Schrödinger equation accurately, but anyway, it was possible. And for having the Schrödinger equation, we can determine expectation value. And this is the plot for the charge radius difference between the beryllium-10 and beryllium-11. And if once it is verified, we can then go to the beryllium-12, which is the proton. Boron-12, which is the proton. Which boron has a proton halo? Boron-14 or boron-12? And then we can study these proton halo, neutron halo isotopes by these atomic spectroscopy methods. So this was the last slide. Let me at the end present my collaborators. In fact, I have a much larger group, but people who we have been working together on this topic is Mariusz Puchalski from Poznań University, my former PhD student, Vladimir Rochin from St. Petersburg, and Wojciech Patkos from University of Prague. Thank you for your attention.
Thank you very much, Krzysztof. Are there questions or comments? Basia?
A comment. Maybe one should mention that one element is lacking in this puzzle.
Which one?
Namely, a direct elastic muon scattering on a proton. And then
I presented the result from Jefferson Lab.
Yes, but this is a very low Q-square. Then you have now the muon proton scattering on in the Swiss experiment.
Yeah, right.
Yes,
because this
is your
experiment.
A new experiment which is planned at very high energy at CERN with COMPASS.
Yes. In fact, I should mention that apart from this atomic spectroscopy measurement, there are two measurements which, in fact, one is at small q square, at PSI, which we muon proton scattering, another one which is compass, which you mentioned. I don't know if they measure directly or they compare with electron scattering.
No, we shall measure directly.
Directly, okay. Yes, and this is, I agree, and probably this most probably is the most reliable determination from the scattering, because we perfectly now understand the what is the problem with scattering. Also to understand this two-photon exchange effects, the second order. But you have to calculate it.
Other questions or comments? Many comments, of course, during the talk.
You mentioned that one needs to use dispersion relations from high energy scattering.
Low energy scattering.
Well, how reliable are such arguments? I mean, this is quite
Indeed.
sophisticated.
In fact, we don't know. We cannot answer this. The only thing we can do is perform the calculation by several groups using different data. It was done. And at least different groups obtain very similar results. This is one argument, but this is not for mathematician. For mathematician, I would say, we don't know. Let's just do it and compare. And this is what you have done. You have done it. This is the result. And compare. And we have the discrepancy, but I mentioned, if one would explain this discrepancy by this, it has to be 10 times larger. Which would look very strange. But this, I would say, not reliable. On your level of accuracy, it's not reliable.
Are there data comparing electron alpha scattering and electron two protons and one neutron scattering to see whether this discrepancy that we have with the isotope shift is also seen with scatterings?
Yes, I already presented this. Let me show you. Let me show you the result. Muonic helium. This is the muonic helium result, and this is the scattering result. Exactly, next slide. Isotope in scattering is this one. Because helium-3, the results for helium-3 are not so accurate. Yeah. So in fact, indeed, one could most probably redo the measurement, but it's much easier to do atomic spectroscopy measurement. In fact, there are several groups working on it now. Yeah, but I should mention once again that this very important, very interesting project with the muon proton scattering. In fact, this is something, it's also a smoking gun experiment. It will show the right value.
So the calculations are sensitive to the charge radius. What about charge distribution? In lithium, you may expect that there will be some more subtle effects. Which element you mentioned, lithium? For example, lithium, I mean, you have 10, 11 nucleons inside.
For electronic atoms, there can be, in fact, the correction which are talking about, which depends on the size, are of the 4-5 orders of magnitude smaller than the leading finite size. At this precision level, it can be neglected. For muonic atoms, it's a different story.
Yeah,
one has to include this.
You probe,
and this is the problem.
The interior.
Yes, and this is the problem for muonic helium, in fact, that is nuclear porosity. This is exactly, by muonic porosity, we mean, I don't present for, let me present for deuterium. For deuterium, in fact, for deuterium is large, and we have to rely on the theory. This is the limiting factor. For helium, it will be much larger. So it's what you mentioned is high order this charge distribution, but it overlaps with the nuclear excitations. It can be combined together, and this has to be taken from the theory. So we believe that we understand the nuclear theory, but this is again, it's kind of the It's not very, we are not sure of it. Let us try and compare. For muonic deuterium, it agrees. How do we compare with the helium? We have to wait for atomic physics experiments, for atomic spectroscopy measurements, to check how the muonic determination agrees with the electronic one. We still don't have the electronic values.
Okay, other questions or comments? Okay.
I have a very stupid question. What would be if electron and muon were not point particles?
Good question. And let me effectively, let's say if effectively we would observe it as a different nuclear charge radius, because we don't know if the finite size comes from the proton or from the lepton. It's the same. So we see its effective charging will add up. It's a very nice example is pionic hydrogen. No, it's not a good example because hadronic particle, sorry. It interacts in the hydrogen. But no, I don't have a finite size particle which don't have strong interactions. Okay, I can give an example. Yes, but I understand the question. This is a structure beyond the standard model, something which is beyond this. For example, if there is kind of structure which is beyond our understanding, will it be visible? No, because it sits in the nuclear charge radius. It will be visible in the electron-muon bound system. It's called muonium. Then we can compare just a pure QED and then a deviation which will signal the finite size of muon or the electron.
It will be visible in high-energy experiment.
Once again?
It will be visible in high-energy experiment.
You're right. Much easier. Much easier. And is it visible?
Okay, one more question.
But you observe the deviation from universality. Okay. But anyway, it's something very similar, just a different interaction with electron muons.
I understand that experiments in muonium are not performed because it, like muon...
just the opposite, just the opposite.
Yes,
no.
So
I have to quote Marek Fitzner, who is the... May I? Okay, Marek is in the ERC committee, and he had just granted a proposal for the measurement of 1s stress in muonium.
Okay, so there will be experimental results from muonium. Cool.
Yes.
Okay, are there any other questions or comments? If not, let us thank Krzysztof again and let us congratulate him again for this very nice achievement. And once again, happy Christmas and happy New Year. Thank you.